So this is a joint work with Aviad and Rubinstein. So let me start by introduce our setup. So in general, we study two-player basing game between two characters of this talk, Jerry's optimizer and Tom's learner. And both two players have a set of actions. Although in this picture, they have the same set of actions. In general, they could be different. In addition, Tom the learner has a private context, which is drawn from a public known prior distribution D. Both Tom and Jerry's utilities are functions that depend on the actions they play and the Tom's context C. If the prior distribution D is a singleton, namely if Tom's context is fixed, then we say G is a standard game. We are particularly interested in the setting where they play this game repeatedly for T rounds. And we assume that, as the name suggests, Tom the learner uses a no-regret learning algorithm. And Jerry the optimizer, knowing that Tom is playing some no-regret strategy, he chooses his own strategy to maximize his total utility. And a quick note, Tom's context is resampled from the area round. And a special case is repeated first price auction. In this special case, Jerry and Tom each has a value for a single item, and Tom's value is context. Each round, these two players they submit their bids, and the player with higher bid wins the item and pays the bid. We study both the general basing games and the special case repeat the first price auction. If Tom's value is fixed in the first price auction, we also call the first price auction standard. If sampled from a prior distribution, we say it's basing. Okay, let me give you a brief overview of the background related to this work. So this optimizer learner setting was initiated by Rubinstein et al. For the specific basing game which you saw in the previous talk. So basically in this game, there is a strategic seller repeatedly auctions an item, a single item, to a basing buyer. And the assumption that one player is using some sort of no-regret learning algorithm rather than always playing perfectly best strategy is motivated by an influential paper that shows bidders' behavior on bid is very consistent with no-regret learning. And their paper showed that if the learner uses a class called mean-based no-regret learning algorithm, which I will talk about a bit later, then the optimizer can exploit these algorithms to extract the full value of the learner. And they also designed the no-regret learning algorithms that are robust to such exploitation. And in the previous talk, you saw another very nice algorithm that also has this kind of property. Afterwards, Deng et al. And Mansour et al. Characterized algorithms that are robust to exploitation for general standard games. And they also made some initial progress towards a characterization of such algorithm for general basing games. So that's a brief overview of the background. Next, I want to unpack a bit about the notion of exploitation and introduce the problems we are interested in. So let me start with this observation by Mansour et al. So they observed that in any repeated basing game, regardless of which no-regret learning algorithm Tom the learner uses, Jerry's optimizer always has a strategy to guarantee himself a Stackelberg utility on average per round. So Stackelberg utility is defined as follows. So in the Stackelberg game G, first, Jerry's optimizer commits to a mixed strategy. And when Tom the learner observes Jerry's strategy, places his best response conditional on his context. And the Stackelberg utility is just Jerry's utility corresponding to his optimal commitment. So in short, Stackelberg utility is the utility of optimal commitment. And therefore, by the above observation, Stackelberg utility is a natural benchmark for this optimizer learner setting, because we know optimizer can always get that. So given this observation, two questions, we are interested in the following two questions. First, can the optimizer exploit commonly used no-regret learning algorithms such as multiplicative weight updates in specific games? In our case, first prize auction. By exploitation, we mean it can beat the Stackelberg benchmark. And to make this problem a bit formal, we need to specify what is commonly used no-regret learning algorithms. Rubinstein et al. Proposed a family called mean-based no-regret learning algorithms, which capture many commonly used no-regret learning algorithms, such as multiplicative weight updates, follow the perturber random leader, EXP3, UCB, epsilon greedy, etc. And essentially, an algorithm is mean-based if in almost every round, conditioned on the learner's context, the algorithm plays an action that has approximately best utility on average in the previous rounds. So formally, our first question is, can the optimizer beat the Stackelberg benchmark against mean-based no-regret learning algorithms in repeated first prize auction? The second question we are interested in is, which no-regret learning algorithms are sufficient and necessary to be robust from the exploitation? By robustness, I mean it should have the property that it can cap optimizer's utility at the Stackelberg benchmark. And you might be wondering, why should the learner care about the utility of the optimizer? And hopefully at the end of the talk, I will convince you the learner should care about that also. And for this question, we studied for general Bayesian games. Okay, so next I want to give you an overview of our results for these two questions. The exploitability of mean-based algorithms in first prize auction and characterizing unexploitable algorithms in general Bayesian games. Let me start with first prize auctions. So we have two results in first prize auctions. First, we show that in repeated standard first prize auction. As a reminder, standard means the learner's value is fixed. Every mean-based no-regret learning algorithm can cap optimizer's utility at the Stackelberg benchmark, which means every mean-based no-regret learning algorithm is robust to exploitation. However, the second result shows that in repeated Bayesian first prize auction, there are instances where optimizer can get arbitrarily higher utility than the Stackelberg benchmark against any mean-based algorithm. So I want to give you some intuition of the second result. Consider the following very simple instance where Jerry's optimizer has value 1 for the item, and Tom's learner's value is drawn from uniformly at random from 1 and 2. First, I want to argue the Stackelberg utility of Jerry in this game is relatively low. Why? When Tom's value is 2, Tom is more willing to bid higher because Tom has more value than Jerry. So Jerry needs to bid extra low with higher probability to incentivize Tom to also bid low, such that Jerry himself can get some utility. But this strategy is not ambitious enough when Tom's value is 1, because Jerry's value is also 1. He would like to raise his bid if Tom's value is 1. As a result, any strategy of Jerry either get high utility when Tom's value is 2 or when his value is 1, but not simultaneously. And that's why the Stackelberg utility is low in this case. Next, I want to argue there exists a strategy for the repeated first prize auction, such that Jerry's optimal utility is higher than Stackelberg utility. And the strategy is as follows. So it has 2 phases. In the first phase, Jerry starts with the optimal commitment strategy against the value 2 Tom. And in the second phase, he switches to the optimal commitment strategy against value 1 Tom. In the sense that if you look at the time horizon, then in the first phase, Jerry's bids will look like the CDF of Jerry's optimal commitment strategy against value 2 Tom, which is the orange curve in the figure. But if you look at the entire time horizon, Jerry's bids will look like the optimal commitment strategy against value 1 Tom, which is a green curve. So if we apply this strategy, Jerry will get almost all the utility he can get from value 1 Tom. And he will also get some utility from value 2 Tom in the first phase. And therefore, the total utility Jerry gets is higher than the Stack-Overflow utility. So that's the intuition of the second result. And let me continue to the second item of our agenda. So I have shown you that bin-based algorithms are not robust to exploitation, even in a very well-structured game like Bayesian first price auction. So a natural question is, are there no regret learning algorithms that are robust from the exploitation? The answer is yes. Specifically, Mansour et al., they proposed a family of algorithms called no polytope swap regret algorithm, which can cap the optimizer's utility at the Stack-Overflow benchmark for any repeated Bayesian games, including the first price auction. And they posed an open question: are these algorithms also necessary to cap the optimizer's utility? Namely, is no polytope swap regret algorithm a characterization of robust algorithms? So before I tell you our answer to this question, I want to give you a conceptual overview of the notion of polytope swap regret, because I think it's a very nice notion to know. So in any Bayesian game, any learner's mixed strategy can be represented as a convex combination of pure strategies. A pure strategy is basically like a vector. For every context, the pure strategy specifies an action, a recommended action. So suppose the polytope on the right corner is a convex hull of the pure strategies. Every vertex of that polytope corresponds to a pure strategy. And for the sake of illustration, I color every vertex, every pure strategy with a distinct color. And then any mixed strategy of the learner just corresponds to a point in that polytope. So what is polytope swap regret? So consider the following realization of the repeated game. And let's suppose Jerry's optimizer's strategy, mixed strategy at round T is alpha T. And Tom, the learner's mixed strategy at round T is beta T. As I just said, we can decompose Tom, the learner's mixed strategy into the pure strategies. We do that for every round. And we say Tom has no polytope swap regret if simultaneously replacing a column in the entire time horizon of Tom's strategies does not increase Tom's total utility. So if you look at this example, if we simultaneously replace all the green strategies with an arbitrary color of the polytope, then it does not increase Tom's value. And the other way to say this is, if we do the thought experiment, let's sample a pure strategy from Tom's mixed strategy for every round. And we look at all the rounds where Tom plays the green strategy. Then in the hindsight, green strategy would actually be Tom's best response. Same for the other column. And therefore, if we look at those rounds when Tom plays green strategy, Jerry cannot get better than Stack-Overflow benchmark. Why? Because we said in those rounds, Tom is playing his best strategy, a best response. And Stack-Overflow utility by definition is the best utility you can get, assuming Tom is playing best response. And so that's the intuition of polytope swap regret. Except I cheated a bit. If you look at the mixed strategy, beta capital T, it is half green and half blue. So in this picture, this point also corresponds to half red and half gray. So the decomposition of a mixed strategy is not unique. So the whole thing I just told you is not well defined. So there's a very simple fix of this. That is, if there are multiple decompositions, then let's pick the decomposition that minimizes the resulting regret. So that's the concept of polytope swap regret. So now back to the open the question whether no polytope swap regret learning algorithms are necessary to cap the optimizer's utility as a Stackelberg benchmark. We show that the polytope swap regret exactly characterizes the exploitability under a necessary technical assumption, which says learner has no negligible context. Basically, that means the learner cannot have a vacuous context that happens with zero probability. Specifically, we proved that if the learner's algorithm A has omega T polytope swap regret in any repeated Bayesian game G, then there exists another repeated Bayesian game G prime, where the optimizer can obtain an extra omega T total omega T utility in addition to the Stackelberg benchmark against the algorithm A. And the learner still has omega T polytope swap regret in the new repeated game G prime. The way I interpreted this result is it shows a higher order zero sumness for general sum games. Let me unpack that a bit. So in any repeated zero sum game, if the learner has regret, then the utility learner regrets not having always goes to the optimizer because the game is zero sum. This is not the case in general sum game, but our theorem says that if the learner has polytope swap regret in any general sum game, then there exists another game such that a constant fraction of the utility learner regrets not having goes to the optimizer. And this higher order zero sumness also shows up a bit in the proof where we used the min-max theorem. And due to the interest time, I will not go over it, but feel free to talk to me offline or check out our paper. Thank you.